Hey physics kids, Campbell here. Today we're going to start our journey into thermodynamics by looking at thermal energy, heat, and temperature. In order to start with thermal energy, we got to go back to last year when we talked about the conservation of energy. Remember we said that within an isolated system, the energy gets converted from one form to another, but the total energy remains constant. So for example, if I store potential energy in this ball and I drop the ball, it gets converted into kinetic energy, but eventually the kinetic energy dissipates. Where does it go? Well, it's not lost to the system, but in fact gets converted into thermal energy. Notice that our thermal energy arrows here are only one way. So the conversion is an irreversible process. So what is thermal energy? Well, what thermal energy is the kinetic energy, so the movement of all the molecules, as well as the potential energy, which are the bonds, the chemical bonds between molecules, or the temporary associations like the intermolecular forces between atoms or molecules in a substance. This is also sometimes called internal energy. So your book uses thermal energy with the E symbol, whereas the College Board and your equation sheet uses internal energy with the U. Now, when we talked last semester, we said we could change the total energy of a system by doing work on it, or the system itself doing work, right? I throw this ball and I apply a force over a distance, which gives the ball kinetic energy. But we never talked really about heat, because we know that if we add heat to a system, if I take a beaker and I put it on a hot plate, the molecules start moving faster, which means that I must have put energy into the system, and I did that through what's called heat. So energy can be transferred into a system or out of a system through work, applying a force over a distance, or heat. So what is heat? The problem is we misuse the term heat all the time. You know, in St. Louis it gets really hot in the summer, so we're like, oh my gosh, the heat is so oppressive, although this summer wasn't so bad. But heat, which is symbolized by a Q, is actually the transfer of thermal energy. It's a process. It's not something we can measure. Temperature is what we're talking about when we say, oh, the heat is oppressive. Temperature is a measure of the kinetic energy of the molecules in a system. This is what we call a state function, because we can actually stick a thermometer in and measure it. But what we're measuring, temperature is actually measuring the kinetic energy. So heat is the flow of thermal energy into or out of a system, but temperature is a measure of the kinetic energy of the system. So let's take a look at that through a simulation here. Now I'm going to put a couple molecules here into my system. I put in little molecules, and what I want you to watch is the kinetic energy of the molecules, right, how fast they're moving, and the temperature. What I'm first going to do is I'm going to put heat into the system like I stuck it on a hot plate or something. And I want you to take a look at the motion of the molecules while I do that. So here we go, firing it up. Notice that the temperature is rising in the system, and the average motion or kinetic energy of the molecules is going faster. Notice that the speeds have increased, but notice that they're not all the same. Right? Some are moving faster than others. They collide with each other and transfer energy, but overall the total energy is staying constant now that I've stopped transferring energy into the system. We can actually do the reverse too. I can take heat out of the system, and as I do that, see, in this case the temperature is dropping, but what the temperature is measuring is the kinetic energy of all those molecules. Notice how their speeds have slowed significantly as I've transferred energy out. And again, the speeds of the molecules vary, and when they collide, there's some transfer of energy between the molecules. Of course, we can go down even farther, and we can slow them down a lot. Go slower. Now they're going very slow. And notice that the temperature is very low. Now this temperature gauge is reading in Kelvin, which is the temperature scale that we will be using in this unit. So heat can add energy to a system and increase its kinetic energy, but we measure that kinetic energy through measuring the temperature of the system. We can remove heat, so heat flows out or energy flows out of the system, which causes the kinetic energy of the molecules to decrease, and we measure that temperature or that kinetic energy decrease by measuring temperature. So how does temperature and kinetic energy actually relate to each other? Well, there's an equation for that. The average kinetic energy, we say average, right, because we saw that the molecules are moving at different speeds, and when they collide, that speed changed as they transferred some of their energy to another molecule. So we call it the average kinetic energy is equal to 3/2 kBT. Kb is actually the Boltzmann's constant, which you can see here is 1.38 times 10 to the negative 23rd. Now notice the units here, it's joules per Kelvin, which means the temperature that we use has to be in Kelvin. Now, if we want to know what the total internal or thermal energy of a gas is, then we need to add up all of these kinetic energies. This is just the average kinetic energy of one molecule. But if I want all of the molecules in the system, then I need to add up all of these. And I would do that by multiplying by the number of molecules. So just a little note, when you see a capital N, I'm talking about number of molecules in the system. How many atoms do I have of a particular gas sample? So I would take my 3/2 kBT equation and multiply by the number of molecules. This would give me the total internal energy or thermal energy of the gas. Now, if you remember back to chem, there was a way of relating molecules and moles, and sometimes we work with moles, so let's take a look at another way we can represent this equation. If we use the number of moles, little n, instead of number of molecules, then we can actually use the gas constant, R, which is 8.31 joules per mole Kelvin. So my big N, 3/2 kBT, becomes little n, 3/2 RT, which means that molecules times Boltzmann's constant is equal to moles times the gas constant. Kind of handy. Now, just a little molecule review in case you don't remember from chem. Capital N is the number of molecules or atoms in a sample, whereas little n is the number of moles. Remember that 1 mole is equal to Avogadro's number of molecules, or 6.02 times 10 to the 23rd. And molar mass, which you can find on the periodic table, is also the atomic mass, is the number of grams in a mole. Now remember, in physics we use kilograms, so that's important if you're working with molar mass. But we also have a direct conversion that goes from the atomic mass into kilograms. So atomic mass, which we symbolize by a U, which we call molar mass when we're talking about grams per mole, we can directly convert that into kilograms by just multiplying by 1.6 times 10 to the negative 27 kilograms. And it's on your pink sheet. Now let's talk more about speed, right? When we were watching that simulation, right, different molecules were moving with different speeds, and those speeds changed every time they collided with another molecule. Well, how do we characterize this speed then? Well, it's actually a statistical distribution given by what's called Maxwell-Boltzmann probability. So this, you'll see by looking at this curve, is it's not a bell curve. So the average is not at the top of the bell. The actual curve of molecular speeds is a little skew-shaped. Now, how do we quantify the kinetic energy then if all of these molecules are moving at all these different speeds, right? Kinetic energy is 1/2 mv squared. So I have to deal with averages, right? And so the average of a sample's kinetic energy would be an average of all of the squared speeds, right? I would take this equation at any instant in time for all the molecules, and I would add them up, and I'd take an average to get that kinetic energy. But this is kind of cumbersome, right? I got to square all these velocities and then take an average. Well, isn't there a better way? Well, there is. If we take a square root of the average, this will actually give me the speed of a typical atom. So we actually have a name for this. This is called VRMS, or the root mean squared speed of a molecule. So the root mean squared speed of a molecule is just the square root of that average, and that would be the typical speed of an atom in the sample. So now if I'm talking about the average kinetic energy of an atom in the sample, I can use this equation. The kinetic energy average is 1/2 mass times the RMS speed squared of a molecule. Well, okay, so now I've got kinetic energy and I have speed, and I had kinetic energy and temperature. So how can I relate temperature to the speed of a molecule? Well, we can do that by taking those two equations and putting them equal to each other, right? If K average is 1/2 m VRMS squared, and that's also equal to 3/2 kBt for one molecule, right? I can rearrange this equation for VRMS speed. And notice my 2's cancel out because they're on both sides in the denominator, and I'm left with 3 Boltzmann's constant temperature in Kelvin divided by the mass in kilograms. So what we see here is that the average speed, or the root mean squared speed of an atom in a sample, is directly proportional to the square root of temperature and inversely proportional to the square root of mass. So that means that bigger masses move slower. And in fact, if we look at the Maxwell speed distribution of different molecules, we can see here that this is oxygen. Oxygen is diatomic, right? So its molar mass is 32. Here is helium, which has a molar mass of 4. And here is hydrogen, right, which has a molar mass of 1. So notice how as that mass decreases, the average speed increases. So lighter molecules move faster. Let's just take a minute to talk about temperature scales, right? Because in the US we use Fahrenheit, but in lab we use Celsius, and in these calculations you have to use Kelvin. So let's look at why. Well, it's really based off what is 0. The zeros set on the Fahrenheit and Celsius scale are kind of arbitrary. I mean, the Celsius one makes sense, right? Because the freezing point of water is 0 degrees Celsius. Of course, for Fahrenheit, that's 32. But on the Kelvin scale, there's absolute 0. So its 0 point is set based off where all molecular motion ceases. So remember that kinetic energy of a molecule is 3/2 kBt. So when T is 0, kinetic energy is 0. That's why when we do calculations in this unit in thermodynamics, we need to work in Kelvin. All right, let's take a look at a sample problem. So I want to know the internal energy of all the molecules in 1 mole of hydrogen at 300 K. Pause the video and see if you can answer this question. Well, we use this equation. I mean, we can use it in this form with molecules and Boltzmann's constant, or of course you could use it with moles and R instead of N and Kb. If you do that, right, it's just a matter of plugging and chugging. If we use molecules, right, you have to remember that there are 6.02 times 10 to the 23rd molecules in a mole, and then we just plug numbers in, make sure you're working in Kelvin, which of course the problem's already in Kelvin, and you should have gotten 3,740 joules of kinetic energy in 1 mole of hydrogen. Let's calculate an RMS speed. So let's take a look at nitrogen. Nitrogen is a diatomic molecule, which means there's 2 when they're bound together, and the temperature is 100 degrees Celsius. Now remember, you have to work in kilograms. Pause the video and see if you can calculate the speed of a nitrogen molecule. All right, so one of the first things you need to do is get the mass of a nitrogen molecule into kilograms. So if we go to the periodic table, right, a nitrogen molecule, or N2, right, would be 14 times 2, which is 28. And that's the atomic mass of nitrogen. So if I use my conversion factor that converts straight from the atomic mass into kilograms, you should get 4.65 times 10 to the negative 26 kilograms, right? Molecules are light, so it makes sense that their kilogram mass is teeny tiny. Now I can plug that in to my RMS speed equation with temperature. Again, make sure you put temperature into Kelvin, so you need to add 273 to that 100 degrees Celsius. So now it's just a matter of plugging numbers in, and don't forget to take the square root. When you do that, you should have gotten 576 meters per second. Holy cow, that's fast! All right, see you in class.